So good morning again, everybody. We're starting our second lecture on thermodynamics and statistical physics. Something it's not working? Fine? All right. Okay, so something that we omitted last lecture, and it's a definition of specific heat. And CV, which are specific heats for us. What do I mean by specific heat? In general, is how much heat was flown into the system or outside of the system, given that the temperature have changed by a specific amount. So basically, it's dq by dt. All right. Now, using the relations that we have obtained on the last lecture, we know that, well, at least we can write it, this type as T dq by T by dt, right? And just multiplied and divided by T. But this guy, dq divided by dt, is basically ds, right? At least for a quasi-static process. So what we have here is that C equals T ds dt. Right? Now, in general, well, we were using specific heats mostly of these two types, but in general, since this is a derivative, but usually what I have in thermodynamics are partial derivatives, right? So I'm going to take this derivative saying that some specific value, for example, of pressure or the volume was kept constant. So in general, Cf is T ds dt, while F is kept constant. And more specifically, Cp is T ds dt, where P is constant and Cv is T ds to dt, and P is kept constant. Okay, so this is just something that we omitted last lecture. Where we actually have stopped, so we stopped when we defined Legendre transformations. Okay, so if we had E of S and V and N, so we know that by Legendre transformation we can obtain several functions. Okay, several functions that are also a function of a state, but the variables are slightly different. So in order to describe equilibrium, describe our state, we don't have always use the energy. We can use Helmholtz free energy, or we can have enthalpy, or we can have Gibbs free energy, or whatever transformation, Legendre transformation of our energy over here. Okay. What we also shown, we shown that delta E is always greater than 0. For example, we keep our entropy constant, okay, and we see if we apply some internal constraints how the energy is behaving. So under any application of internal constraint, what we are getting is an increase in the energy. We also claimed that we cannot differentiate between application of internal constraint and then releasing the constraint and a spontaneous fluctuation of the system to exactly the same state. Right? So basically, what this principle of minimal energy means is either we apply constraint, internal constraint, and then the energy is going up, or there are some internal spontaneous fluctuation, and under any kind of fluctuation the energy is also going up, right? So this is the principle of minimality of energy, and we obtained it basically applying the second law of thermodynamics. one can show, and you have been given a home assignment to actually show it, that for all Legendre transformations of the energy, okay, also the free energy is minimal, and the enthalpy is minimal, and the Gibbs free energy is also minimal. Okay. So any variation, spontaneous fluctuation or application of internal constraint, also are giving rise to all the others functions of state. Okay. And the proof is exactly the same as the proof for energy, exactly the same thing. Now, so what we know so far, we know that we have a function that dictates what is our state. We assume that the function, any function of a state that we are going to use, is minimal in equilibrium. And we also know that the entropy is a monotonically increasing function of energy. And we assume something about, well, continuous properties of the function. Basically, in thermodynamics, most of the time we assume that our function of states, like energy or the other functions, are continuous. We change our parameters slightly, and the function is also changing somehow in a continuous fashion. Moreover, if we are already talking about functions, we can assume something about analytical properties of those functions. For example, that their derivatives are continuous, or even more, that the second derivatives are continuous also. Now, this assumption about continuous properties of the function leads us to something which is called Maxwell relations. So as we have seen, we don't always want to use energy because, well, it's hard to express everything using energy or using entropy. Now, since we're assuming this continuation, we sometimes want to relate different properties or different derivatives of the function by one variable to the other variable. Now, if we assume continuation and continuation of derivatives and continuation of second derivatives, we can use the theorems that we once learned in calculus. What do I mean by that? So, for example, we have a function f of x and y. And I assume it's continuous, and it has continuous derivatives, and it has a second continuous derivative, etc., etc., etc. So I can write its differential as a dx plus b dy. Okay. Now, a is a function of x and y, and b is a function of x and y. So if the second derivatives are continuous, basically what I can show that dA to dy, keeping x constant, specifically equals to dB to dx. Okay. Why it's actually? Well, one must remember that A is df dx and B is df dy. Keeping x constant, keeping y constant. So what I have used is that d squared f dx dy equals d squared f dy dx. The order of differentiation doesn't matter as long as the derivatives are continuous. So basically, if I assume that my functions of state, either energy, free energy, enthalpy, doesn't really matter, if they have continuous derivatives, I can relate their derivatives to the derivatives of some other variables. Now this is important. Why it's important? Because, think about that. What is dE? TdS minus P dV. And for example, we have plus mu dN. We have only one component, only one type of particles. So T is dE to ds. right? And minus P is dE to dV. Here we keep constant V and N. Here we keep constant S and N. Okay, so if I'm assuming all these continuous properties of my state function, I can use this relation over here, okay, and say that dt to dv, right, equals to minus dp to ds. Okay, here what I'm keeping constant, here I'm keeping constant s and n, and here I'm keeping constant v and n. Okay. Now there's huge number of different mathematical relations which are all of them, they are all called Maxwell relations, and all of them are based on the fact that we assume something about continuous properties of the second derivatives. That's it. Now, since there are many such relations, I just will present some of them. So for an additional example, we have for the free energy. So dA, we know, is minus S dt minus P dV plus mu dN. Okay. What I know from here is that derivative of S with respect to the volume equals to the derivative of the pressure with respect to the temperature. Okay. So ds to dt, I'm sorry, dV, keeping T in a constant, equals dP to dt, keeping V and N constant. Now, why it's sometimes important? Because this property over here, I can actually measure. Okay? In an experiment, I can have a control. I don't have control of entropy. But I do have control of pressure, and I do have control of the temperature. Okay? So by controlling and observing this quantity, I can also say something about how entropy changes with volume. Okay? So basically, what those Maxwell relations they are good for is that I can relate properties that I don't really have control of them, okay, to the other properties and variables that are controllable in experiment, and so this is the way of actually how you can measure them. Additional example. For example, the Gibbs free energy. So dG equals minus S dt plus V dP plus mu dN. So here we have ds dP t and n equals minus dV dt t and n. Now I can continue with game all day long, performing Legendre transformations and and establishing relations between different quantities, different derivatives. Now, this is something, well, yes, you can go measure this guy and then obtain something about entropy, but in itself, it's not always very informative. Why? Because those are partial derivatives. Now, in order to build a function of x and y, there are very strict conditions how I can build this function knowing only partial derivatives. Okay? It's usually not enough to know just the partial derivatives, but we will see that specifically in our thermodynamical world, which are very simple, very continuous, we'll see that the knowledge of partial derivatives is actually sufficient in order to establish what is the state function, what is my energy, or free energy, or enthalpy, or Gibbs free energy. They're enough. The knowledge about what are and how the partial derivatives behaves completely defines how the function of state behaves. We'll get to this in a couple of minutes. In the meantime, I want to present, by using those Maxwell relations and some other games, I will present you two results that will actually later will become very useful and important. And in order to establish those results, they are related to specific heat. I will use those Maxwell relations. Okay. So I'm back to my specific heat. And I know that CV is equals to T ds dt while keeping V constant and the number of particles, or number of moles, constant. All right. Now, sometimes it's important how the specific heat is actually changing with the volume, right? So I want to compute this guy, dCV to dV, while keeping temperature and the number of moles constant. How I do this? So I'm just basically saying it's T. Let's write it down. So it's d to dV of T ds dt. I'm keeping V constant, number of particle constant. And when I'm making a derivative with respect to the volume, what I'm keeping constant? The number of the temperature constant and the number of particle constants. Okay, so I can get T out of this equation. So it's simply T dV, keeping T constant and N constant, and ds to dt, keeping V constant and N constant. Okay, now my assumption about all of these thermodynamic quantities is that the derivatives are continuous, and I can switch between the order of differentiation. So it's simply T d to dt while keeping V and N constant of ds to dV while keeping T and N constant. Okay. Now, what is ds to dV?
dP over dt.
dP over dt, right? This is what I already got over here. So this guy is T to dt of dP over dt, keeping V and N constant, and d to dt, keeping V and N constant. So generally I obtain that dCV to dV of T and N constant equals to T and second derivative of, with respect to the temperature, of the pressure, keeping V and N constant. Okay. We will find that this actually will become important, if not today, maybe in the next lecture. Additional example. Okay. So we had already the specific heat with constant volume. Let's see what is the relation between specific heat of constant volume and specific heat of constant pressure. So what is the specific heat of constant pressure? Is Cp, as we know, d ds dt, constant P and N. Okay. And here we will perform a slightly different game, right? But again, it's a game of changing variables and keeping one variable constant and then changing it and keeping another variable constant and assuming all of this continuation properties. All right, so here we have this formula, and if we're keeping the number of moles constant, what is the differential over entropy? So we know what are the variables. The variables are temperature and the variables are volume. So we can write that the change in entropy is the change of entropy with respect to the temperature, V and N constant, dt, keeping N constant, plus this partial derivative of S with respect to V, keeping T and N constant, dV. Now, let's change our variables. So here the variables are t and v. What if we would write to describe v in terms of t and p? Okay? How the differential of v will look like? And in all of this discussion, we're keeping the number of moles constant. So what happens here? So the differential of the volume with respect to pressure and temperature is simply dv to dt, keeping p constant, dt, plus dv to dt, keeping what we keep here constantly, keeping it here, dp. Now those are not really interesting, lengthy calculations, but this is the thermodynamics of the 19th century. A lot of assumption of continuation, a lot of derivatives. Eventually we will get there. A little bit of algebra on the board. Right, so what we can do now is we can take this dv and introduce this into this equation over here. Okay. Where we're getting that ds n constant is ds dt v and n constant dt and constant plus ds dv d and n constant, and here we have d, let's write it over here, we have all of this, so it is dv dt p dt plus dv dp t dp, right? Now see, we have here dt, and it's always with constant n. We have dt and dp, our new variables. Perform the change of variables on the level of the differential. Okay? What we do, we gather around whatever we can. So we have that ds, constant n, equals to ds dt, v and n, plus ds dv, t and n, dv dt, p and n, all of this multiplied by dt, constant n. Plus we have the additional form, which is ds dv t and n multiplied by dv to dp of t and n. Okay, and here we have dp constant n. This calculation is not very exciting. It's a little bit long, but eventually one gets some useful stuff. All right, what is the next step? So the next step will be
S over the P to VDP as the S over the P.
what of this guy?
Yes.
Yes. We'll get there. You're absolutely right. But this is only, we can perform this substitution. It's the same variable, right? So for example, here we are not doing it. We are not allowed to do this because it's ds dv dv dt. But here the constant variables are t and n. Here the constant variables are p and n. So they're different. Okay, so what we are getting here, this guy over here is simply ds to dt with constant p, right? And this is what we were hoping to achieve from this relation. Right? So we take this And we write it in the following fashion. So we have ds to dt of constant p equals to ds of dt of constant v and n plus ds to dv of constant t and n multiplied by dv to dt of constant t and n. Okay. So what is this guy? It's just simply 1 over t cp. What is this guy? It's 1 over t cv, right? ds to dt, constant volume. Okay. So we are left only with this ds dv t and n, dv to dt p and n, and we cannot just simply say is ds dt p and n. Why? Because the different variables over here. This is the game. Now, how or what I can say about a function, or about two functions, when I perform such a switch of variables. Okay? So this is something that we all knew when we studied in our first undergraduate year. Calculus, but usually we forgot it, because it's not very useful. So let's see. If we have x as a function of y and z. Okay, so the differential of x, dx, is simply dx dy constant z dy plus dx to dz constant y dz. Right? This is a simple simple transformation. But if we have also, we can express z as a function of x and y, right? So we can express the differential of z as dz, and we have dz to dx constant y dx plus dz to dy constant x dy, okay? And we take this dz and substitute it over here. And substitute it over here. So what we are getting? We're getting, any questions? No? So what are we getting? We're getting that dx is dx to dy constant z dx plus dx dz constant y, and here we have a multiplication instead of dz, dz to dx constant y dx plus dz dy constant x dy. This is good in some sense. Why? Look what we have here. We have dx dz multiplied by dz dx. The constant variable is the same. Okay, so what we have here, dx dz dz dx is simply dx dx. All of this guys cancels out. So we have here that dx equals dx dy z dx plus dx plus dx dz y dz dy x, right? Dy. Dx dx goes away. Dx and dx goes away, and eventually, what we have here? We have here, what is my relation? Dx dx. Here I had, I'm sorry, so here I had dx dz, it's a dy over here. Because we had dy over here, so it's the same dy over here, and we have dy over here. Okay? Now we can also divide both sides by dy, then the dy and dy disappears. And we're getting that dx dy z equals minus dx dz y dz dy x. Some lengthy calculation. Okay, so now you see what we are having. We are having that dx dz dz dy is simply dx dy z. We are going backwards. We're going backwards. And we're submitting, or by using this formula, what we can say. We can say that dp dt with constant v and n is always constant in this example, is simply equals to minus dp dv, constant t and n, dv to dt, constant v and n. Okay? Okay, so what we had here? We had here that dcv dv, no, we were over here. So back to this equation. So we have 1 over cp, 1 over tcp equals 1 over tcv plus ds dv plus dv dt. Now ds dv, we know what it is, right? What is ds dv? We already got it somewhere, someplace. So ds dv is simply dp dt. Yes? So let's rewrite it again. 1 over t cp equals 1 over t cv plus, instead of ds dv t and n, we are writing dp dt, dp dt v and n, dv dt v and n. Okay. Now we are taking this dp dt v and n and we are substituting this guy. Okay. And this is, and we are obtaining the following relation, that cp equals cv minus t dp dv t and n and dv dt e and n squared. So it's a little bit lengthy calculation, not very interesting. You only substitute different variables by other variables. But those guys experimentally were quite interesting. So dp, and we also will see afterwards why they are interesting for us, specifically for the case of phase transitions. So dp dv, it's isothermal compressibility. And this guy, it's called thermal expansion. Why it's interesting? Well, because we see those functions are specifically, the specific heats and the thermal compressibility and thermal expansions are quite usable. They're also measurable quantities. But the whole point of this calculation was to show, wait, you have a function of the state, you can play with it, you can play with the differentials, you can play with the second derivatives, and everything can be matched. What I mean by, well, not everything, but all the quantities or all the variables that you sometimes do not control them, and you want to express their changes by using some other partial derivatives, you actually can. Now, but as I said before, you cannot always define the function by only the knowledge of its partial derivatives. But there are exceptions to this rule. And what are the exceptions? The exceptions are homogenic function. Okay. Where I'm just trying to use this description of, well, we're using this mathematical calculus of many variables, and we're trying to use it as far as we can, as long as we assume something about our functions of state. Basically developing a little bit of a rules, how you can define, declare, what you can do with your functions of state. Now, so now for this Maxwell relations, we use the continuation of the derivatives. But this only defines us relations between different partial derivatives. It does not define for us what is the energy of the system, or what is the free energy of the system, or the enthalpy. But if our functions were homogenic functions, actually the knowledge of partial derivatives is sufficient. And what I mean by homogenic function was already defined by Euler. A homogenic function is a function where I multiply its variable by some constant lambda, and there is this kind of scaling relation. So g of lambda x equals to lambda to power n of g of x. Okay? N is the order of the homogenic function. So for example, if g of x equals 1/2 x squared, okay, g of lambda of x equals 1/2 lambda x squared equals to lambda squared 1/2 x squared equals lambda squared of g of x. So this polynomial, very simple polynomial, is a homogenic function of a second order. Right? Very nice. Now, not all the polynomials are homogenic functions, but there are some functions, very specific, that have this specific property. Now, for a homogenic function, what kind of homogenic functions we already seen? Actually, all the functions of state are homogenic function of the first order. Why? Because we know that energy and entropy and all of the other functions of state are extensive. Okay? So if we have two subsystems, we know that the energy is E1 plus E2. Okay? Basically, this means that if we have x as our extensive variables, for example, variables that define the size of the system, and we transform them into lambda x, okay, we know that E of lambda x is transformed into lambda E of x. Okay? It basically means that the energy is the linear function of the size of the system. So if we have this property, we know that energy is a homogenic function of the first order. Now, this is important because it's even more specific class of homogenic functions. We will see. What is temperature? Is it a homogenic function? Yes.
Zero.
Of order 0. Yes. We change the variables of the system, we change its size, but the temperature does not change. Right? It's an intrinsic property. Okay? It's an intensive function. So all our variables and all our functions were homogenic functions. The extensive functions or the extensive variables are homogenic functions of first order. The intensive variables are homogenic functions of the second order. 0. I'm sorry. Okay. Now, happily enough for the physical world, the mathematical world, there was this guy named Leonhard Euler, which done fantastic job in all different parts of mathematics and physics, specifically create for mathematics or for homogenic functions. He had this wonderful theorem. Okay? I will skip the proof of this theorem. I will just state it and will publish the proof on Moodle. It's pretty straightforward, and maybe you've already seen it somewhere. So the theorem for homogenic functions of first order, or Euler theorem of homogenic functions of first order. Luckily for us, all our energies or all our functions of states are homogenic functions of the first order. So how this theorem goes, let's use this board over here. So if g of x1 to xn is a homogenic function, okay, the number of variables we don't really care about, i.e. g of lambda x1, lambda x2, lambda x n equals lambda g of x1 to xn, then g can be expressed by its partial derivatives. So g of x1 to xn is simply a sum from I goes from 1 till n dg dxi all xi. Here we'll have all other variables are constant. Okay. So this is a nice property. The only thing that I need to know in order to describe a homogenic function of the first order is its partial derivatives. Okay? It completely defines what the function looks like and how it behaves. And this is exactly our situation, right? Because we know what are the partial derivatives, or sometimes we can control them, right? How we know them? Because we have written our, for example, let's take, for example, the energy. Okay? So the energy we obtain from the first law and the second law. And we know that dE, okay, dE equals to TdS minus P dV plus mu dN, where in general plus I goes from 1 to n mu I dNi. This is our energy. How we obtain it? We use this conservation of energy. and the second law for the definition of the entropy. Okay. Now we know that energy is extensive function. If we know that energy is extensive function, it's a homogenic function. And if it's a homogenic function, the only thing that we need to know in order to say what is the energy is the partial derivatives of this function. And what are the partial derivatives of the energy? It's T, P, and all the mu i's. How they are related to different other, or their properties are related to different other variables, well, we know the Maxwell relation. But the knowledge of those guys is enough, because E is simple Ts minus PV plus a sum of I from 1 till n, mu I and I. And we can do exactly the same thing if we know energy. We know enthalpy, we know free energy, we know Gibbs free energy. Why? Because we transform energy to all the other functions of states by the means of Legendre transformation. Okay? Knowledge of the energy exactly defines knowledge of all the other functions. Knowledge of the other functions exactly dictates knowledge of the entropy. Okay? Now, if we know this, we can again use some chain transformations for the variables, etc., and obtain additional relations for different quantities in thermodynamics. All of this assuming what? All of this assuming very important stuff. All of this assuming that everything is continuous, right? We're in some specific phase that we change the variable and nothing drastic happens. We will see a little bit later that it's actually not true. Sometimes. Okay, but meanwhile, if we have this nice representation of energy or any other function of a state, the same way as we played with Maxwell relations in order to get some maybe non-interesting relations for us, but they were interesting 100 years ago, we can do this exactly the same with this energy over here. How the games goes. So we say, okay, so if this is the energy, what is the differential of the energy? Okay. What is the differential of the energy? So it's simply TdS plus SdT minus PdV minus VdP plus a sum of I from 1 to n mu I dni plus a sum from I to, alright, let's write it over here, plus ni d mu I. Okay. This is simply taking a differential of this guy over here. But over there is another definition of the differential of dE. So this guy on the left side equals exactly what is written over here. It's equal to TdS minus PdV plus a sum of I from 1 till n mu I dni. We cancel a lot of stuff out, right? Because TdS and TdS over here goes, and minus PdV goes, and eventually we are stuck with S dt minus V dV plus a sum of from I to n of ni d mu I. This guy equals 0. And this important equation is called a Gibbs-Duhem relation.
What's the name of the second one? Gibbs what?
Duhem. D-U-H-E-M. actually we can use this relation in order to obtain some intuition what is Gibbs free energy. Okay. So remember, Gibbs free energy was equals to E minus Ts plus PV. Okay? This is the definition of Gibbs free energy. So it is simply, since we can now say what is E. E is Ts minus PV plus this is the sum. So let's substitute. So E is Ts minus PV plus a sum from I from 1 till n mu I ni minus Ts plus PV. Now Ts minus Ts disappears, minus PV plus PV disappears, and we obtain that the Gibbs free energy is simply the sum of different mu I and I. And this is simply the Gibbs. For n equals 1, we obtain that Gibbs divided by the number of moles in the system if we have only one particle, single component. We obtain that Gibbs divided by n is mu. So our chemical potential is the Gibbs free energy, or Gibbs free energy per mole is the chemical potential of the system. Right? Relation between one type of energy and how it's described. Okay. Now, up to this part was thermodynamics, classical thermodynamics. Everything is continuous. You change your value of your parameters a little bit, you obtain a different functional state. Everything is related to everything. You can connect different states by quasi-static process. Everything is in equilibrium. Very, very, very nice. You can obtain different properties of gases related to the other gases. This stuff works wonderful. And this is what you already probably knew, or at least learned it from a different perspective in the classical classes on thermodynamics. But in reality, we know that this continuation property and that everything can be very simply connected from one state to another state, it's not always true. Okay? We know that there are different phases of matter. Okay? And this is our next step of in our lecture. It's called equilibrium states. We know that if we have a gas or we have water, container of water, it's an equilibrium. Okay. But if we will start to heat it up at some point, we have water, it was an equilibrium, we do not change the temperature, we do not do almost anything. We change, for example, the temperature a little bit, it's still water. Change the temperature a little bit, it's still water. Reach, for example, with the pressure of 1 atmosphere, we reach 100 Celsius, and what we start to see, or near 100 Celsius, that our water is actually, some of it became gas, and here we had water. Something occurs, and pretty much dramatic, in the system. Okay? It was water, it was behaving in a very specific fashion, and once like that, instead of water, we had gas, by heating the system. And this change is something that occurs for the naked eye in a discontinuous fashion. So part of all of this continuation properties, etc., doesn't really work. Okay, so there are specific situations when we change our equilibrium steady state, and by an infinitesimal change properties, or by infinitesimal change of the internal parameters, the state of the system, as we see it, changes dramatically. Those changes we say, or we declare to call them phase transitions. And specifically at the phase transitions, part of all of this thermodynamics starts to fail. Okay? Because it assumes something about this continuity of matter and continuity of interactions, and its phase transitions those assumptions does not always work. You can see that sometimes functions can have a discontinuous change, or their derivatives can have a discontinuous change. Okay, now, so maybe all of these Maxwell relations do not work, or some state functions do not behave as we would like them to behave. But if we use so far this theory of analytical functions, the theory of continuous change, well, we can continue to use it, but we will just use mathematics that at some points those functions do not have continuity, or their derivatives do not have continuity. Still, the framework can be the same. So what we are going to use now is to use the same framework as we were using before about continuous changes and continuous relations, but we would actually explore what can happen to the system near specific states, near specific points when the functions are no longer continuous. And this, by exploring this property that the functions, state functions are, or their derivatives, are not exactly continuous, we can obtain something about what happens to water, or how this transition between different phases of matter can occur. So we're now going to this subject of equilibrium states and phase transitions. Any questions? You're really quiet today. Either it's very, very simple and trivial, so I can speed up, or you do not understand anything.
I just don't understand, like, the math is fine, I just don't really understand
where the physics, or where we're going?
Yes.
Okay, so we're, up to now, I was covering what you already know, or supposed to know. And it was just a bunch of results. We were trying to describe thermodynamics from this mathematical perspective. Where we're going now is to use the same math and to use the same perspective in order to describe equilibrium and transitions between different phases. This is where we're going right now. Okay. Right. Okay. So, in order to describe equilibrium states, I will need to use some assumptions. And the first assumption that I already been using it extensively so far is the extensivity of energy. Okay? Because think about it, where I'm actually going. I will try now to say I have a system, and in this system I have two states, or two phases of matter that are in equilibrium with each other. For example, I have water and I have gas. Or I have water and I have ice, right? Now, I want to describe the situation which is close to equilibrium, okay? Which is close to equilibrium. And those two states are in some equilibrium situation. They are in equilibrium. The thing is, when I'm describing a system that has several phases at once, I'm assuming that the energy of the whole system can be described by the energies of one phase plus the energy of the second phase. It's like I had two systems in previous lecture, and I say, well, the total energy is always E1 plus E2. I can say exactly the same now. I have two systems, but instead of I have two phases. And the total energy is the energy of this system plus the energy of the second system. Now, there is something funny about it, and what is exactly funny is that when I connect two systems, there is an interface. Or I have two phases, there is always an interface. right? For example, I have a container, and I have water down, I have gas. On the upper side, they're somehow separated, right? And then there is an interface between the two phases, or the interface between the two systems. In order to describe something about equilibrium, I need to describe something about the energy of the total system. I'm using this assumption of extensivity, but what if actually this interaction energy between the two systems is important, right? It can be really important, because I can say, well, the interaction may be dependent on the size of the interface, right? So do I actually neglect something when I'm using this assumption of extensivity? The clear question, yes, of course. Why? Because if I had two particles, a green particle and a purple particle, okay, what is the total energy of the system? Is the energy, self-energy of this particle plus the self-energy of this particle plus some interaction between the two guys. So for two particles, my extensivity property is not working. Okay? Why I'm extensively using it for all thermodynamics in the last lecture, and in this lecture I will use it too. Okay? Why I'm neglecting for macroscopical objects this interaction energy between the two systems or between two different phases? And the answer is, well, you can do it in a lot of cases as long as your system is large enough. Right? So it's a reasonable assumption under specific conditions when the system is big and huge. And I will use some hand-waving arguments and scaling in order to describe to you why it's applicable. Sometimes it's not. Sometimes the only thing that matters is the surface energy. And then we cannot just say, well, everything is extensive, because then we're only observing what happens on the interaction. We will see it later in the class. But if I'm only considering the bulk energy for a macroscopic object, this assumption of extensivity is almost precisely correct. Now, how this argument goes? So consider a box. Okay? So it's a square box with size L by L by L. Okay. Now, I'm claiming that the energy inside this box is proportional to the number of particles inside the box. A lot of different particles inside, and the total energy is proportional to the number of particles. Okay? What is the number of particles? The number of particles is the concentration multiplied by volume. Okay? Very simple argument. Now, let's assume that I'm keeping the concentration constant, and I only can play with the volume of the system. So, for a three-dimensional object, I know that the number of particles goes as L to the third power. Okay. So L goes to N to 1/3. Okay. Now, what is if I had a box and now this box is separated into two subsystems, and I'm looking on the interaction energy of the surface between the two systems.
So you're saying that because there's a small amount of particles on the interacting.
Yes, this would be exactly the claim.
But it might be a huge interaction.
If they are short range.
Who said it's short?
Okay, wait. I said, but wait. Okay, so what is the size or what is the surface of this guy? Okay, the surface is L squared, right? This is the surface. L squared. Since L goes as n to the 1/3, L squared goes as n to 2/3. Okay. Okay, and here the claim. So the energy in the bulk is proportional to the volume, or the proportional to the number of particles. So bulk, E bulk, goes as n. Okay. The energy of the surface proportional to the number of particles in the surface. And it goes as E surface goes as the size of the surface, and it goes with the number of particles to the n to 2/3. Okay? Now, let's assume, or let's continue with what you're saying. I have a proportionality constant over here. This is the interactions between different particles. So here I can have a very big constant. You're perfectly right. This is why, okay, but I don't really care about this constant. Okay? I completely don't care about this constant because the total energy is E bulk plus E surface. Okay? So it's actually, we can say, well, E bulk is some constant A, it's approximated like this, multiplied by n. And here I will have some additional constant to n to 2/3. Right? Let's get n out of the picture. So I have a n, 1 plus b, n to the power of n b divided by a, n to the 1/3. And maybe I have some additional corrections. But those additional corrections are go with n even with a smaller power. Okay, this is like a dimensionality claim. I don't really care as long as the moment as n goes to infinity, okay, I completely don't care what this constant is. Okay? Now think about it. What is n approximately? Avogadro number. So n, we're talking about the size of 10 to the power of 24. This is as large as n can be, and even larger. Okay? So for a macroscopical object, this correction, even if b is very, very large, okay, and have other different interactions, etc., since this guy is extremely small, okay, it's 10 to the minus 7, it does not contribute almost anything. Okay? This is why this extensivity claim it works. But it only works for macroscopical objects because only there we can say we have huge number of particles.
Why can't b be of the size of 10 to the power 10?
Okay, so if we are talking about some extremely large interactions, this stuff stops working. And this starts to actually occur at the phase transitions. Okay? So what you're saying is, Actually, if the interaction is really, really huge, but it's not always happening, or the surface or the interactions in between all the different particles. So this claim about locality does not work. This claim about locality is saying I'm interacting with some small group around myself. Okay? Only then it's linear. But if I'm interacting with everybody, this claim is also not working, and this is what happens at phase transitions. Additional case if the interaction is extremely huge. So if this is the case, and if the interaction is so huge that you take one particle, change it a little bit, and it really affects the total total energy of the system, then it's again not feasible, this extensivity assumption. But for regular situations, when the interaction is not so huge, this n to the power 1 minus 1 over 3 is a really small parameter. This is the small parameter of the system, and it's smaller than everything else. In statistical mechanics, this type of claims, dimensionality claims, or they call the scaling claims, are quite often applied. So we don't care about the system. We hand our waves a little bit, hands a little bit about the dimensionality properties and how one property goes with the other property. And using the scaling, we say, well, one parameter is large, is dominant, the other guy is really, really small, and we won't care about it. Okay, so this was the part of why I can use extensivity, because I actually need to use it. Extensivity of energy, extensivity of entropy, extensivity of a lot of different parts. Okay, so stating that, I would now like to say something about stability properties of equilibrium. Okay. So when I'm claiming that I have two systems that are in equilibrium with each other, okay, so I have system E1 and I have E2. Okay, so let's assume that gas, water, were just two systems in contact. When I'm saying that everything is in equilibrium, I actually claim that there are no macroscopic currents. So the energy, the total energy stays constant. There is no flow from one system to another. And as I look on the system for long enough times, nothing really changes. Remember how I define equilibrium. It's a stable state, and I can define it with a small number of parameters. Okay? So equilibrium between two different phases or two different systems actually means that there is no flow of anything between those two systems. They're in equilibrium, no macroscopic flow. This phase stays as it is, and this phase stays as it is. So what are the conditions? What are the conditions in order to sustain this property, this stability? Okay. So what we are going to do now is define or obtain the properties or the stability properties of two phases or two systems. Where I'm going to phase transitions. How I'm doing it? I'm placing two phases next to each other and saying the system is in equilibrium. So first, let's find the condition for equilibrium of two different phases. What was our major tool so far? So a lot of mathematics of many variables, first and the second law, and this variational principle. Okay, what was this variational principle? The variational principle stated you change something, or the entropy was at its maximum, the energy was its minimum. The minimum and maximum with respect to what? With application of internal constraints, or with due to spontaneous fluctuations. Right. So what we are claiming now is if this guy is in equilibrium, we want to apply this variational concept to it. We will change the system a little bit. We will change system 1 a little bit. We will change system 2 a little bit. Totally, the system is not changing. For example, the energy stays constant. There is some mixture between those systems, and we claim that any kind of such mixture, spontaneous or induced by internal constraints that we apply, will increase the total energy of the system. Okay? So basically, we are going to use the energy is minimal at equilibrium in order to say something about the conditions for this equilibrium. How exactly I'm doing this in general? So basically, I'm going to say I had a system which has a constant entropy. It had some extensive parameters, and its constraint was 0. And I created a constraint which is non-zero. Let's call it delta y. Okay. This is what I created. Now, what I know that delta E, which is equals to E prime S x delta y is my constraint, minus E S x 0 constraint is greater than 0, as long as my constraint is internal. Or I can say here delta y is the small spontaneous fluctuations that occur. Okay. I'm at equilibrium, I'm at the minimal energy possible. So, but what is this delta E? What is this delta E? Basically, we can Taylor expand it, right? So delta E equals to dE dy delta y, right?
Don't we say that the energy decreases?
The energy increases. Energy is at minimum.
Right. Oh, it was in equilibrium and
It was in equilibrium, I applied a constraint, the energy have grown. Okay? Plus 1/2 dE to dy squared delta y squared. Plus etc. 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 This is what we understand as simple Taylor expansion. In this language of variations, delta E is delta E, first variation, which is what? Is simply the derivative of energy with respect to y, plus a second variation of E, which is basically the second derivatives of E with respect to different y's, plus etc. 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 What we are going to explore is the first derivative, the first variation, and the second variation. The same can be applied to further variation, the function, etc., etc. But we will see that since delta E is greater than 0, exploring the first variation and the second variation is sufficient in order for us to obtain some conditions about equilibrium. Now, if delta E is indeed in minima, what is going to be dE to dy? It's a minima, so what is the first derivative? 0. Okay. So the first variation is actually no variation whatsoever. The second variation should be either 0 or positive. Okay. But let's first look at what happens when we explore that the first variation should be greater than 0 or 0 by definition. How we do it, how we introduce this constraint, how we write all of this math over here in the fashion that we already been doing before. Let's write it down over here. What is delta E? It's greater than 0. So delta E is the change of, sorry?
Can you explain again what you wrote here?
Over here?
Yes.
So I'm saying when I'm changing E, the change of E in the language of this variational calculus is the first variation plus the second variation plus the third variation.
So
what are those?
Delta E is a variation.
This is the change and delta is a variation. How it's described in terms of variables, it's a simple Taylor expansion. Okay? So for you, when I'm saying I'm performing a first variation over a second variation, I'm just saying I have taken this first guy in the Taylor sum. or I have taken the second term in the Taylor sum. Okay, that's it. So what is delta E? Remember, I have two systems. Right? E1, E2, S1, S2, N1 and N2, for simplicity. They were in equilibrium. Now, something totally or globally, or I can also have V over here, V1 and V2. Let's assume I'm not changing the energies of the system, but I have allowed for some exchange of the entropy, for some exchange of the volume, and some exchange of the number of particles. Okay? But delta S general equals to 0, delta V general is equals to 0, delta N is equal to 0, so nothing changed on global scale. Okay? But this means that delta S1 equals minus delta S2. And delta V1, delta V1 equals minus delta V2. And delta N1 equals minus delta N2. So when I'm saying that I applied an internal constraint, I need to take the first derivative of E with the application of this constraint. I don't know how to write equations. I have booted a wall here. I'm saying I have changed an entropy a little bit of this guy, and I have changed the entropy a little bit of this guy. I have changed the volume of this guy, and I have changed the volume of this guy. And I have changed the number of particles of this guy, and I have changed the number of particles of this guy. But those changes are somehow related. Why? Because total change is 0. I have done nothing with the system. Okay, so what is this point over here? Is simply dE1 to dS1 delta S1 plus dE2 ds2 delta S2 plus dE1 dV1 delta V1 plus dE2 to dV2 delta V2 plus dE1 dN1 delta N1 plus dE2 delta N2 delta N2. Right? Those are my variables. The constraint change them somehow. I don't really know how. I know that those changes are somehow related. And I write the first derivative as simply the expansion due to this in the Taylor form. What term? Up to what term? Up to a linear term. Now all of those partial derivatives I already know. I know them already. What is dE to ds? T. Okay. So my delta E equals T1 delta S1 plus T2 delta S2. Okay, this is the first one. dE to dV is minus P, right? Remember, what is the differential of energy? Is TdS minus PdV. So dE to dV is minus P. Minus P1 delta V1 minus P2 delta V2. Okay. And the third guy, what is dE to dN? Is mu, the chemical potential. So I have here plus mu1 delta N1 plus mu2 delta N2. Okay. Think about it as a first order expansion, Taylor expansion. Okay. Now let's take those relations over here and apply them. Okay, we have delta S1 minus delta S2, delta V1 minus delta V2, etc., etc., etc. So what we're getting that it's T1 minus T2 multiplied by delta S1 minus P1 minus P2 multiplied by delta V1 and plus mu1 minus mu2 multiplied by delta N1. And all of this is greater than 0. Always. What I mean by always, no matter how I apply the constraint, no matter what was the fluctuation that changed the different extensive variables of the two systems, okay? The change in the energy should be positive. Now, I can arbitrarily change delta S1. I can arbitrarily change delta V1. I can arbitrarily change delta N1. They are not related to each other. When is this always, this inequality is always holds? When it's 0, right? So, we are getting that T1 equals T2. And P1 equals P2. And mu1 equals mu2. Those are our equilibrium conditions. So in order for two systems to be in equilibrium with each other, or in order for two phases to be in equilibrium with each other, all of this must be conserved. And when this conserves, so the system is in equilibrium, delta E is actually not greater than 0, it's simply 0. And that's what I told you already, we could guess from the start, because we're saying E is a minima. So if E is a minima, and the first variation is just the first term in Taylor expansion, the first term in Taylor expansion around minima is always 0. But those are equilibrium conditions. We already know, or have seen, that, for example, we take two systems and we make them in contact. They had different temperatures. So, if they had different temperatures, the heat will flow from a higher temperature to a lower temperature. Okay? If we contact two systems and they have different pressures, okay, there would be exchange in volume. Okay? So one system will pressurize the other one till the pressures are exactly equal, and the volume of one system will change. And one system it will grow, of the other one it will decrease. The same with the chemical potential. When we attach two systems, okay, and there are differences in the chemical potential between the two systems, there will be flow of what? Of mass from one system to another. Okay? Because again, it's always an equilibration of energies, or equilibration of those guys by flow from a higher concentration of T or higher T to a lower T, or from a higher P to a lower P. And the same happens with the chemical potential. Okay, so we have two systems and they are not in contact, and we have a system with a higher mu and a system with a lower mu. Mu1 is greater than mu2. What will happen if we will make them in contact and we'll wait till equilibration? So particles from system with a higher chemical potential will flow to the system of the lower of chemical potential. What will happen? At some point the chemical potential will equilibrate and will be equal to each other, and then the flow will stop. The moment there is some change or there's some macroscopic difference between the chemical potential, we again obtain a flow till the system equilibrates again. Those guys are also called in the literature thermodynamical fields or thermodynamical affinities. Because think about it as if we have a gradient in a field, okay, like in classical mechanics. if we have a gradient in the field, we put there a particle, the particle will decrease till the gradient is 0. Okay, so there is to the point where there is no force. The same happens here. When there is a gradient of temperatures within the system, the whole system will flow to the point when there is no gradient, no differences between the different temperatures. The same happens with pressures, the same happens with chemical potentials. So the equilibration process is basically equilibration or equalization of different intrinsic properties of the system, or intensive variables of the system. Okay, we will stop over here, and in 20 minutes from now, we'll continue and explore the second variation in order to get additional constraints or additional conditions for equilibrization. We're returning to our expansion, and just to remind you what we managed to achieve so far. We managed to achieve by actually observing what is the first variation of the energy. We managed to achieve the conditions for equilibrium. Okay. So, and what we see that for between two systems or the same system but two different phases, the equivalence of temperature, pressure, and the chemical potential is essential. And what we also notice that this first variation of the energy is strictly 0. And you already knew this because energy is at its minimum. Right. Now we can follow the same procedure and try to say something about the second variation. So this guy is simply goes to 0. So we can also say if the first guy is 0, then the second variation, delta square E, must be positive. Okay. So if actually this wasn't true, so the first variation wasn't strictly 0, we don't really know, or the conditions for the second variations are somewhat arbitrary. They probably will depend on the first variation. But since the first variation is strictly 0, we can exploit this fact, use this fact, and we will see that it actually gets us some nice results. Now the difference between the results that we obtained from the first variation and the second variation is that the first variation actually says something about what are the conditions at equilibrium. The second variation will tell us what are the conditions to reach equilibrium. Okay, so we'll see it in a second. All right, so how do we do it? We do it in exactly the same fashion as we have done it for the first variation. We are expanding it to the second derivative. Okay, so the first variation is described by partial derivatives of the first order. The second derivative, the second variation, is described by partial derivatives of the second order. Okay, now since here there are no, when we describe the first variation using the derivative of the first order, we only had those guys over here. So d ds, d dv, and de to dn. When we are going to establish the conditions from the second variation, we will have d squared to d s squared, for example, and s1 squared, and we will have d squared e1 to ds1 to dv1, and we will have plus d squared e1 to dv1 dn1, etc., etc., etc. So we will have a lot of mixtures of different partial derivatives, and since here we have already 6 terms, doing all of this expansion for 3 variables in and I'm actually writing down all the mixture of different derivatives is actually powerful. Instead, we're going to limit ourselves to a slightly lighter condition. So if beforehand we allowed exchange in S, allowed exchange in V, and we allowed exchange in N, what we're going to do now, we're going to allow only exchanges in S. Okay? And we will see where it will lead us.
I have a question.
Yeah.
You said that the second variation can be 0, but if it's 0, then
the third variation should be positive.
Yeah, it won't.
And it will continue on. No. Yes. Yes. Indeed. Now, there are specific conditions under which the second variation is 0, and then it continues on and on. It's not really interesting. So mathematically, it's fun, but it's not really interesting. Okay. So what we are saying, we have two systems, and what we have done is we are looking S1, S2. B1, B2, N1, N2. Now we allow only, we're keeping everything constant, we allow only the change of the entropies. Okay, so delta N1 equals 0, delta V1 equals delta N2. Delta V1 equals 0 equals delta V2. And delta S1 equals minus delta S2. Okay. So there is only exchange in entropies, there is no exchange not in volume and not in the number of particles. Okay. Now we write our second variation. So how it looks like, it's the second variation of E1 plus the second variation of E2. So what's the second variation of E1? It's 1/2 delta squared of E1 plus delta squared of E2. Now the second variation, where we only changing one variable, varying, okay, not changing, we varying only one variable, it's simply a second partial derivatives. So it's d squared of E1 ds1 squared delta s1 squared plus 1/2 d squared E2 over ds2 squared delta s2 squared. Okay. This is the second variation. Okay. So first of all, we can take outside 1/2 delta s1 squared, right? Because delta s1 equals minus delta s2, but squared, we don't care about the sign, right? And inside we have d squared E1 to ds1 squared plus d squared E2 ds2 squared. Okay. What is d squared E to ds squared? So we can write it down as d to ds of, what is dE to ds? T. And what is dt to ds? dt to ds is d divided by cv. We keep keeping the volume constant in this system. Remember, delta V1 equals to delta V2. The volume is constant, so it's dE to ds when V and N are constants. So it's dt to ds. When v is constant, so it's t divided by cv. Okay. So let's write it down inside this equation over here. We obtain that the second variation, delta square E, equals to 1/2 delta square delta S1 squared T1 divided by CV1 great T2 divided by CV2. And this guy is greater than 0. Should be greater than 0. Now, for the previous argument, we say everything should be 0, or we can control delta n, delta s, and delta v in any form that we want. This means that all the arguments between the variations of the variables should be 0. Here, we can control delta s as we want. It's arbitrary, but it's positive always.
So also this term.
So this term must be positive. Okay. But we want something about a single system, right? Here we have a sum of T1 divided by CV1 plus a sum of T2 divided by CV2 greater than 0. Now, we can even say, well, we know from the first variation that the temperatures are are equal and positive. We know that temperature is a positive thing. Okay, so we can take this thing out, or we can say take the temperature out. But still we have 1 over CV1 plus 1 over CV2. I want eventually to say something about how a system, I told you why I'm exploiting the second variation. I want to say something about how the system reaches equilibrium. Okay? Now, what I'm going to claim is, well, let's look on CV. What is CV? CV is d ds to dt with a constant volume, right? So CV is an intensive variable, temperature, multiplied by the extensive variable divided by an intensive variable. So CV is extensive or intensive? Extensive. It's proportional to the change of S. So it should be dependent on the size of the system. So it's extensive variable. Okay. If it's extensive, it can become small or large if we change the size of the system. Okay. Right. So the larger the system, the larger is CV. The smaller the system, the smaller is the CV. Okay. Now, when I started over here, what I obtained here is two terms. Okay. And I had some arbitrary differentiation of the system. I have system A and I have system B, or phase A and phase B. I haven't told you who is large and who is small. The thing is, since the sizes are arbitrary, I can always say, well, actually what I was doing, I was looking on one system that is large and one system that is small. So if CV is proportional to the size of the system, 1 over CV for the large system is very small, and 1 over CV for the smaller system must be large. Basically, 1 over CV is proportional to 1 over the system size. And since I can control the sizes of the system, I haven't said anything about, well, the sizes are equal. Or one system must be larger and one system must be smaller. Okay? Since I can control the sizes of the system, I can say, I can always choose two systems for which one of those terms is dominant. Okay? It's much, much larger than this guy. Why? Because CV, T is exactly the same, and CV is proportional only to the size of the system. Okay? There is a constant of proportionality, but we are talking about large systems. Okay? So there is always, I can choose it in such a form that there is always a dominant part to this sum. Which means that this dominant part, T over CV, must be greater than 0. Okay? T divided by CV is a positive constant. It's not constant, it's a positive thing.
Sorry.
Yeah.
What if CV is less than 0?
Is less than 0. So what will happen over here?
So I think the temperature can be more than 0 and...
The temperature is positive. Let's start from this point. It's positive. The temperature is positive, we know that, because it's Z to ds in the second law of thermodynamics.
So while CV is negative, so this cannot be...
No, so if CV is, look, if CV is negative, let's assume that CV is negative. Let's follow your lead. So if CV is negative, all right, now one of those guys is very large and negative, the other one is very small and negative. Okay? Because I can define the size of the system. I will take one large system and one smaller system. Okay? So one would be 1 over big negative, the other one would be 1 over small negative. But both of them are going to be negative. There's still a dominant part. Okay? The smaller system is going to be smaller or larger and negative, and this is going to be smaller and negative, or the other same around. But the sum is going to be negative. And if the sum is negative, it actually cannot be larger than 0. And this must be satisfied always. Okay? So that's actually leads. So if I'm assuming that CV is negative, okay, I cannot be at this minima of the energy. My second law of thermodynamics have collapsed. Because where I came to this idea that the energy is minimal, it's a direct outcome of the second law of thermodynamics. Okay? So E is minimal, the second variation is positive. Think about it, I have a function and I expanded it in a Taylor series around its minimum. The second term has to be positive. Okay? And this is exactly the second term. If CV is negative, it follows apart. Okay? You can also think about it, what is CV? How we define CV? We started that C in general, the heat capacity, is the change of heat by the change of temperatures. Okay? So positive CV means the heat flows from high temperature to low temperature. Negative CV means it flows the other way around. Okay? Now, so think about it. You have a difference in temperatures, then the system with the higher temperature starts to heat itself due to the heat of the colder system. So the hotter is becoming hotter, the colder is becoming colder, and they do not reach the equilibrium. The equilibrium is when the temperatures are exactly the same. If CV is going to be negative, they won't reach this equilibrium because the temperature's gradient will only grow. Right? So this is what I meant is how the system approaches equilibrium. This guy can be approached only if CV or this guy is greater than 0. Otherwise, the gradients will only grow larger and larger. Okay? And we can obtain all different other quantities by exploiting the second variation of enthalpy, of free energy, of Gibbs free energy, and all of them will tell us something about how equilibrium is reached. So, if those are equilibrium conditions, in order to reach them, I need CV greater than 0. This we show. Okay. We can also show, and you will show it in your homework, that CV is greater than 0, and that minus dP to dV is greater, Tn is greater than 0, and there is some other constant that will say how the system reached equilibrium. So those are equilibrium conditions. In order for them to be satisfied, when we start from gradients, so differences between different t's and different u's, those conditions are actually guaranteed that eventually we will reach equilibrium. And in general, I won't prove it to you, but there is a general statement about how intensive quantities are changing with extensive quantities. So if I have phi, a function of state, it can be energy, enthalpy, Gibbs energy, Helmholtz free energy, okay? And x1 to xr are extensive variables, and I r plus 1 to IL are intensive variables. So d phi is written by a sum from I from R to R II dxi minus a sum of j from r plus 1 till n of from xj dij. This is my differential. Following the same prescription as I was presenting over here, but using much longer math, but it's exactly the same math, I can show that dii dx I is always greater than 0. And those conditions are sufficient in order to get to equilibrium. It's not a complicated task, it's just a long one. So what we have achieved so far, we achieved the notion of how equilibrium looks like and how we reach equilibrium. We have conditions for equilibrium, and we have conditions to reach equilibrium. So great. Now, why we started all of this discussion? So this discussion started because in order to somehow explain, or this is at least what I told you, how phase transitions occur. And now, what exactly I mean by phase transitions?
How do you get this minus there?
So consider that I had an energy, okay, and I somehow Legendre transformed it. Okay? So general function of state, R is arbitrary. It can be n and then I don't have those terms. But this is achieved through Legendre transform. Okay, where was I? Right, so phase transitions. Now, in phase transitions, we are assuming that there are two phases. The phases are in equilibrium with each other, and we want to see, because all of thermodynamics that we are looking on is an equilibrium thermodynamics, and statistical mechanics is also going to be in equilibrium. So there are two phases. Now I'm making a small change in one of the parameters and suddenly jump to the other phase. I increase my temperature and a different phase of matter occurs. I know how to reach equilibrium, or I know what happens in equilibrium, and I know how I should reach equilibrium. So basically what I know, if two phases are in equilibrium with each other, those conditions must be satisfied. Now I'm going to start or explore those conditions, okay, in order to say something informative about what is, from thermodynamical perspective, a phase transition. what exactly happens when actually water is boiled and it's evaporated in the gas phase. Okay. So if I have a constant energy, okay, if I have a constant energy, this means that I can have chemical potential can be described by temperature and the pressure of the system. What I mean by that, I have a manifold of a constant energy. My variables are, or I know that my parameters that I can control are chemical potential, the temperature, the pressure, and I know that if I have access to the temperature and I constrain it, and I have access to the pressure and I constrain it, I can find a mu that will depend solely on the temperature, on the pressure. Okay? What it means if I have T and I have P, I can plot this two-dimensional function, mu of T and P. So if this is mu, I know that there is some manifold, a two-dimensional manifold, that describes how mu is changing with T and P. Think about it as a two-dimensional sheet. Now, it's a continuous function, and also it's continuous everywhere. Okay. Or we assume that it is continuous everywhere. But what can actually happen? We notice that in some space, or space of T and P, this function mu behaves differently. So there is region when T and P is actually described a little bit differently than the other regions. Okay. So everything can go smooth, then nothing happens, on all the derivatives are smooth, but actually there are lines for which mu is continuous. So if we cross this line from this description to this description, okay, mu is not changing, not by a bit. Okay, it's continue. The changes continue. But if you look on the derivatives, or the second derivatives, or the third derivative, sometimes you will see that they are actually discontinuous. It can happen. Okay, why I'm claiming that mu is continuous? Because well, I'm going to claim that this is going to be phase A. This is going to be phase B. The chemical potential in phase A and the chemical potential in phase B. This is a coexistence line. So on this line, the chemical potential is described exactly the same if the system is in phase A or it's in phase B. It doesn't really matter. The chemical potential, if the system, the whole system, is in equilibrium, the chemical potential of phase A and phase B should be exactly the same. Okay? If I am in this case, there's only one phase. If I'm in this case, I'm only in other phase. But here, two phases can coexist with each other. Right? It's only in this case that the chemical potential is described in exactly the same fashion by chemical potential of one phase and the chemical potential for the other phase. This line is called coexistence line. It basically means that there are regions in space when two phases occur. Okay, for example, at a specific pressure, and at boiling temperature, I will have vapor and I have water together in the same system. Right? They both coexist and they can both be in equilibrium. So, by exploiting or exploring what happens at this coexistence line, I can somehow understand the properties of phase transitions. Now the key point is that I associate a phase transition with some discontinuity of the derivatives of my chemical potential. Okay? I'm saying something drastic happens inside the system. It was water, it had a specific order, I boiled it, and it became vapor. Okay? So by my eyes I see the change, and I claim that this change, mathematically speaking, can be associated with specific jumps, not with this function itself, because the function itself must be constant, two phases coexist, but this doesn't mean anything about the derivatives of this function. I'm saying at phase transition there is a specific jump in the derivative. But before we will start to talk about this changes in mu, let's look on the coexistent line itself. So what is the dimensionality of this coexistent line? We have, in order to describe what this line looks like, we have mu of t, mu alpha, or mu a, of t and p, equals to mu b of t and p. Right? This is the equation that dictates that the two phases are in equilibrium. The temperatures are exactly the same temperatures, so this is the condition for our equilibrium on two phases. It happens only on this coexistent line. So how many variables we have for this equation? 2. How many equations do we have? 1. So the number of variables minus the number of equations are number of free parameters that describe the coexistence line. Okay. So it's 1. There is one single parameter that describes the coexistence line. So the dimensionality of the coexistence line for this case is 1. Okay. So this is basically, we're saying that the coexistent line is one-dimensional.
That can be more than one-dimensional if it's a line.
If we had additional constraints. So here, it's a line, but it's not always a line. Let's assume that I would have several different kinds of particles. Right? If I had several different kinds of particles, then those chemical potentials must be equal for different particles as well, or different kinds as well. And then I will have more parameters, and I would have more equations, and I will have a higher dimensional structure. Okay. But if I have only one kind of particles, then this claim is correct, and it's only a line. This is why it's called a coexistent line. But if, for example, I have two kinds of particles, it's going to be already something else. I will write the form. Okay, so if this is a one-dimensional line, if we plot T and P, okay, if we plot T and P, we know that there is a line that separates phase A from phase B. Okay. And as you said, line is simply one-dimensional. Now, this I wanted to find a point in space or in my phase space where the two phases coexist. Can I have a situation where three phases coexist? For example, water, vapor, sorry, liquid, vapor, and crystal, so ice, right? Can I have a situation that where three of those coexist? The answer is yes. What will happen over there? So I will have a third phase, and I will write that I have mu A of T and P equals mu B of T and P, and mu b of T and P equals mu c of T and P.
So it's a point.
I have two variables, two equations, it's zero parameters. Zero parameters with zero-dimensional object. I will have only a single point. Right? For example, like this. And here I will have phase C. Okay? So for a system where there is only one component, one type of particles, their maximal number of three phases, and there is only one point when they can coexist. This is not exact. This is not true when I have larger number of particles, not particles, types of particles. Okay. So there can be different structures over there. Right. Now, we will see that there is transitions from one phase to another, and also over here. And this critical point is actually can be very interesting. For example, even for water and ice and vapor can coexist at only one specific pressure and specific temperature. This is not true for coexistence, for example, of water and vapor. They can coexist in different temperatures and different pressures. The boiling temperature depends on the pressure. But there's only one specific point when you can transit slightly from water to liquid, from liquid to vapor to ice. In general, there is a rule. It's called Gibbs phase rule. So the Gibbs phase rule states the following. F is dimensionality of the coexistence line equals 2 plus R minus gamma. R is the number of different types of particles or molecules, and gamma is the number of coexistent phases. Okay. How we obtain? This is called Gibbs phase rule. This guy over here. How it's obtained? You write all these conditions of equivalence of different chemical potentials. You count the number of variables, and eventually you obtain this equation over here. It's not really informative because we usually do not treat systems with a lot of different types of particles, but from this equation you can see that the situation when we have two particles, two different types of particles, three different types, the situation becomes much more complex. It's not a simple line as we draw over here. It becomes a hypersurfaces, and they somehow can cross each other, and three phases and four phases can coexist, etc., etc., etc. So this is how the phase line, how we determine if it's a line, not a line, if it's surface and not a surface. So we just stated that there is something that's going on in the phase itself. But as I already told you, at the line itself, let's go over here. At the line itself, we expect something to happen. We expect some discontinuity in chemical potential. Right? This is how we say Otherwise, well, we change the temperature, we change the pressure, and nothing really happens. We change it a little bit, nothing really happens. But we see in experiment that there is a drastic change. We do see this. So what actually happens? What happens to the mu? What can happen to mu? Okay. What we need to show is if mu itself must be continuous. Why? Because the phases are in equilibrium, but the equilibration or equilibrium properties do not tell us anything about the derivatives. The derivatives themselves can jump. Okay, so let's see what is actually the derivative of mu with respect to t and of mu with respect to p. Why we are doing it? Because we are expecting for the derivative to behave funny, and if they behave funny, maybe we can actually go and measure it and say this is actually a signature of phase transition. So what is, or how we obtain the derivatives of mu with respect to t or p? We are going backwards to our Gibbs-Duhem equation. So what is Gibbs-Duhem? Is S dt minus v dp plus mu dn, n d mu equals 0. So we see that we can, from this equation, obtain what is the differential of mu. Is mu S divided by n dt minus, minus 4, plus v divided by n dp. Let's write S over n as S prime and v over n as v prime. So S prime is basically the entropy per mole, and V prime is the volume per mole. Okay. So from this equation, we immediately see what is the derivative of mu with respect to t and of mu with respect to p. Why? Because if we write d mu, we will say it equals d mu to dt dt plus d mu to d p dp. Okay. This is a simple differential of the chemical potential. So what we obtain that d mu to dt, while we keep p constant, equals minus s prime. Okay. And d mu to d p, keeping t constant, is v prime. Okay. Our conditions for equilibrium say nothing about the derivatives. At this coexistence line, mu must be continuous. If you're coming from here, we in this phase, or we're coming in from here, we in that, we in phase B, the chemical potentials are exactly the same. But but nothing from the equilibrium conditions says anything about the derivative of mu. So the derivative of mu over here is S prime A. The derivative of mu over here is S prime B. If we're crossing this line while keeping p constant. Okay? Sorry, minus here and minus here. So we cross this line, we're keeping p constant, we are only changing t. Okay? And we observe on this part S prime SA. Okay? The entropy per mole is SA. Here the entropy per mole is SP, S prime B. And since the derivative of mu do not have to be constant, do not have to be continuous, we can observe actually a jump in the intrinsic entropy or the entropy per mole. Okay? It will change drastically and not a continuous fashion. The same holds for d mu to dp. Okay? We are keeping the temperature constant, we're changing the pressure, And in one phase, we had one specific volume. We changed the pressure a little bit, and we crossed to another phase, and the volume jumped. Okay? Think about it as I start from water, and I go up and I heat the system. Okay, so I'm changing the temperature, and I'm keeping P constant. I'm changing the temperature, so my single particles, the entropy per particle, is how one single particle behaves on average. It's the disorder. They all behave, there is not a lot of noise, they all wander somehow. Coordinated motion. I cross the boiling point, and suddenly it's a gaseous space. What happens? Each particle don't care about the nearby particles. Any one of them is a simple random walker. It just drives around like crazy. Okay? Doesn't care completely about what happens to the other guys. So my entropy have the disorder, the noise, is actually jumped in one single point. Right? The same can go for the volume. Okay? I was in water or I was in gas. I've kept temperature constant. I increased or decreased P, and suddenly I'm a free particle in a gas, and suddenly I'm in a liquid state, and I already have all those guys around me, all those water molecules around me, and I have to somehow move together with them, and I already have less space to move because I have to move exactly like this molecule that nearby me is moving. So the volume is also jumping. Okay? And we observe this in experiment. This is the molecular differences between the two states. So in order to observe this, we see by, oh, this is water, this is gas, but something happens on the molecular level also. And how we measure it? We measure it as actually a jump for this chemical potential. The local volume, the self volume, or the self entropy. But this is actually when the first derivatives jump. We can say, well, actually you can have a transition of two different phases, and the chemical potential is continuous. The first derivatives are also continuous. Nothing really jumps. But the second derivatives can be discontinuous. Or the third derivatives can be discontinuous. Okay? So, in general, we define the order of the phase transition. So, the order of phase transition is the order of this first discontinuous derivative. Most situations that we are familiar with, or for example the water-gas transition is a first-order phase transition. We do see an abrupt change in the properties of entropy and local volume. But there are other transitions. We can find specific transitions which are going to be of the second order. They're called the second-order phase transitions or continuous transitions. Why continuous? Because nothing actually jumps. Something else happens in the system. Okay? And, well, now we only define them. In the next lecture, we actually will show how to find this transition coexistence line. And later on, when we also cover some properties of statistical mechanics, we will see what really happens on the level, on the microscopical level, for the first order transition and the second order transition. And second order is actually much more interesting than the first one. Although, nothing really jumps over there. So, we'll continue next time.